Hello all, this video is to serve as documentation for the demo that took place during ETH New York 2019, where we recently demonstrated a major milestone in proof of location technology by processing and validating a presence claim over radio. At Foam, we are building what we call proof of location, and are creating an architecture that can be summarized as follows. Layer 1, the root chain. This is where the incentivization for producing and validating location data, presence claims, can be governed using smart contracts on the Ethereum blockchain. Layer 2, sidechain. The data produced can be transmitted to and validated on a local blockchain and produce cryptographically proven presence claims. Layer 3, radio. These are consumer radio hardware that runs a Byzantine fault-tolerant time synchronization protocol in a mesh configuration over the air with cryptographic signatures. Today, Ethereum suffers from what is called the scaling problem. Transactions are costly and slow. Scaling solutions, such as Plasma and Tendermint, allow workarounds, and we have therefore embarked on an architecture that fulfills the needs of Foam's radios to operate with fast and low-cost transactions within the zones themselves. Previously, we have shared information about the GeoPickle testnet, which allows us to perform simulations and testings of Layer 1 and 2 with a virtual Layer 3, in this case represented by a rack of 40 Raspberry Pis. The demo outlined in this video demonstrates the first time we used a Layer 3 running over radio, and thus replacing the virtual Layer 3 of the GeoPickle. We consider this a major milestone for Foam. The important demonstration here is that the radios commit proof of time synchronization and that the logs that they commit are compatible with the signatures used for participation on both the root and Plasma chain that the users and the radios communicate over. In this demo, we used the LoRa 1276 as a zone anchor prototype alongside a development board and the microcontroller. We have developed a custom firmware for the transceiver boards which implements packet transmission and reception with relatively high resolution timestamps. This allows for messages to be precisely timed for inclusion in the blockchain, enabling the necessary information for localization to be communicated to the blockchain aspect of the stack. Transceivers can only operate on one channel, so for this demo each zone anchor has 4 transceivers and a Raspberry Pi. Future iterations of the demo and the Foam developer kit under development will utilize the LoRa SX1301 gateway chip, which can operate on multiple channels at once. The general outline of this demo is the following. 3 radios are consistently engaging in a time synchronization protocol over radio, and thus have the ability to locate a user within their reach. They have formed a zone on a Plasma sidechain and staked tokens to guarantee their fulfillment on the protocol. A user enters the zone and wants to request a presence claim. The user transfers tokens to the Plasma sidechain and burns their tokens there. The radios see the request, logs the exact time that it was received, and validate the presence claim. For this, they are rewarded with the tokens that they can claim on the root chain. In exchange, the user has a presence claim signed by the radios that is valid with respect to the logs posted to the sidechain, a cryptographic fraud-proof claim of where they have been. We built a simple front-end web interface which shows the status of the Plasma child chain as it pertains to the root chain, i.e. Ethereum, which is where the Foam token is staked. The front end shows the logs from the radios coming in and where they can be staked. The front end utilizes MetaMask to interact with the Ethereum and Plasma blockchains. What we will see in the demo is that a user wants to establish its location, it can talk to the radios, i.e. zone, request a presence claim, and see the transactions happen on the front-end interface. As mentioned, the Plasma front-end interface utilizes MetaMask, and for the first step the user will need to register with the Plasma blockchain. First, the user deposits Ethereum tokens into the Plasma contract. The deposit is then displayed in the Plasma contract. The user now has an unspent UTXO. In place of a more advanced escrow smart contract, for this demo we are simply burning the UTXO so it cannot be double spent on the root chain. By signing a message, the UTXO gets included on Tendermint. The burn requires signed confirmation because in the event the user tried to reinstantiate their tokens on Ethereum, it would be fraudulent and not allowed in the Plasma architecture. The user can now request a presence claim to be validated over radio and on the Plasma chain. The second step is that a zone is created. So simultaneously, a zone is created. Zone creation is represented through the signing of a UTXO on Tendermint. The zone needs to register with the Plasma operator as well when it runs its time synchronization protocol. Phase 3 is that the user creates a presence claim, and presence claims are submitted. A zone anchor can now assign a presence claim that it is registered with the operator. The logs are submitted from the radio as a proof that the presence claim is validated. The fourth phase is that the presence claim is valid. The user can now access their presence claim in the interface. Once validated, the zone anchor will be rewarded a UTXO that can be transferred to the root chain. Once the Tendermint hashes containing these transactions are posted to the root chain and are verified, the user's burnt UTXO is distributed to the zone anchors as payment for the presence claim.